All right, so we're back with video 4, and this time we're going to start our first attempts to calculate enthalpy using one of the methods. And so what we're going to start today with is we're going to try and figure out enthalpy with calorimetry. And I've put a nice little red box, congratulations to me on that, to let you know this is what we're doing. So what is calorimetry? Well, calorimetry is figuring out changes in energy in a calorimeter. So this right here is a calorimeter. And the most janky form of this is just a styrofoam cup that's nested, because styrofoam cups are pretty good at keeping energy in there. And what you do is you put some sort of liquid. Typically that liquid in here is, I know, water, because that's something that's really common. And then we stick a thermometer down in, and we have this cool little stirring arrangement here that we can kind of rotate back and forth. And when we do that, it kind of stirs the stuff that's inside here. And what can happen is if we have liquid and then we throw something else into that liquid, we can see how much that temperature changes. And that's the essence of a calorimeter. Now, there is a go-to equation that is the big equation, and it's called the heat equation. And this is the heat equation right here. It is Q equals MC change in T. We affectionately call this Q equals MCAT because it kind of looks like an MC and then an A and a T. Well, what are each of these variables? We're going to go Christmassy all in here. This is heat, and this is heat lost or gained. And we typically measure that in joules. This is the mass of whatever is being heated or losing heat. That mass is measured in grams. This is called the specific heat, and this is what makes things work. And the units are kind of tricky here. It is joules per gram degree Celsius. Now, if you take a look at the previous page, and I should have just left this out here, but if you guys can take a look here, this is a tag or a list of the different specific heats. And what this joule per gram degree Celsius is, this is the amount of energy in joules. Remember, enthalpy is just a fancy way of saying energy, right? Or change in enthalpy is another way of saying change in energy. So whenever we have to apply a certain amount of energy in, this is the amount of energy that's required to raise 1 gram of something 1 degree Celsius. So if we have, for example, water has a really, really high specific heat, which means it takes 4.18 joules of energy to raise 1 gram of water 1 degree Celsius. So imagine you had a pot, I'll draw a pot here, and it's full of water, right? There's going to be many grams, so many grams of water in there. And if you want to raise that from room temperature up to 100 degrees Celsius, do you realize you have to put a lot of, that's a flame right there of my stove, underneath that to raise that temperature up, because each individual gram requires 4.18 joules of energy just to raise it 1 degree Celsius. So when we come back here to our equation, this means this. This is the amount of energy that's required for any specific material. So every single material has a unique specific heat. Change in temperature, that is your final temperature minus your initial temperature. And whenever you're doing a change, it's almost always, almost exclusively final minus initial. So if you ever find yourself going, what the heck do I do next? Change in temperature is always final minus initial. Now, it should make sense, but let's go back to specific heat for a second. We said it's the amount of energy that it takes to raise 1 gram of pure substance by 1 degree Celsius. Now, it would make sense if the specific heat is lower, the lower the specific heat, the greater the temperature change when heated. Because it would require not very much energy to cause a temperature change, because that's on the top. The higher the specific heat, the lower the temperature change when heated. So if you were to heat two things the exact same amount, so let's say you had one thing, let's make this water, right? And that water has a specific heat of 4.84. And on the previous page, and I'm going to just glance back, let's take carbon, or actually let's take mercury, because who doesn't like to boil mercury in their home, right? Let's take the most deadly thing that we can think of. This is mercury. And mercury has a 0.14 joule per gram degree Celsius. This is joule per gram degree Celsius. So in this case right here, for every gram of this water, it's going to require 4.84 joules to raise it. So let's say we put in 1,000 joules of energy into both of these, right? If we put 1,000 joules of energy, and I probably should have drawn on the bottom. Again, this is my flame. I don't know why I'm using red on red, but let's say this is the amount of energy being inputted. This is the amount of energy being inputted. Here, for every 0.14 joules, I raise the mercury 1 gram per degree Celsius. Here, for every 4.84 joules, I raise it 1 gram. So would you agree that if I put the same amount of energy into both of these, the one with the higher specific heat is going to raise its temperature a lot lower than this would? And by the way, an added bonus is that mercury, while in liquid form, doesn't mess with us at all. If we were to raise mercury's temperature to boiling, whatever mercury's boiling point is, which you shouldn't find out, now you'd have gaseous mercury floating around, and that is extremely deadly. So that's a perfect example to show a high school class. Let me drive this home with one more example. It's the hot summer day that we have in Texas. You may have heard of those. Unless you're out at a pool and you ever done a thing where you're sitting comfortably on one of these lawn chairs over here, that's you, and I was going to draw you, but I realized it's kind of hard to do on a black surface, a black background. So that's you sitting over here, and you're all wonderful, and then you want to like run. I don't know why you wouldn't go jump directly in, but let's say you wanted to walk all the way through here, and so this is you on the edge, and you are with your feet walking on the very, very hot cement, and you have an unhappy face because you're walking on it's going to be ouch, 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 ouch until you jump into the water. And why is that? Well, water specific heat is 4.184 joules per gram degree Celsius. So this sun, which is providing all the energy, I've drawn a delightful sun up here. This sun that's providing the energy down in here is beating down both on the water and on the cement. On the water, it requires 4.184 joules to raise the temperature 1 degree, which is why when you jump into the water, maybe it's 80 degrees or 85 because we're in Texas and it's 100 and something outside, 1 million, whatever the temperature is. But the concrete itself has a much, so this is a high specific heat. The concrete has a very, very low specific heat. So maybe it's like, I don't know, 0.2. That's a total make-believe number. I'm sure that I could have Googled that. I'm sure some of you will just to let me know. 0.2. So that means that same sun heating up the concrete is going to jack up the temperature huge on the concrete, where it's not going to jack up, this is little arrows, it's not going to jack up the temperature quite as much on the water. Now, let me also remind you of the units that we use for change in enthalpy, or Q. Now, notice we're going to use on the previous page, we made this assumption. We said the change in H is equal to Q, and we put this little P down below to mean that that's at constant pressure, because everything's kind of constant pressure, because if you're outside, the pressure isn't going to change from where you're walking from the chair to here. The pressure is going to be 1 atmosphere of pressure no matter where you are. So the units we use for enthalpy versus just regular Q are this. It is kilojoules per mole. So typically we do this and we figure out Q in kilojoules, but the actual change in enthalpy, they always do it per mole for some reason. Now, how would we solve for the change in enthalpy, which is again kilojoules per mole? Well, we do this. Q is equal to MC change in T. That will give us our energy. Now, be really careful, because when you do this normally, our Q is going to be in joules. Joules are a really small number, so kilojoules is 1,000 of that. So we go from joules of Q to kilojoules. Moles, we were familiar with it before, because haven't we over and over again converted between grams and moles? We've done this all the time with like molar mass. But then haven't we done other problems where we've had like limiting reactant problems where we are given A plus B and it goes to C, and one of these is the limiting reactant, and then we form a certain amount of the product, and whatever that is, that could be in grams, and then we could convert it to moles or whatnot. There's more than one way to get from grams to moles, but just be aware that the bottom here is always kilojoules per mole. So if we have a certain kilojoules and we divide it by the number of moles, we're going to end up with a change in enthalpy for a reaction. Now, the best way to even talk about this is to do an example. So I'm going to do an incredibly basic problem with you guys here. I've mathed this in advance so you guys don't have to worry about it. I'll put my arm in front of the camera here. So here is the problem. Now we're going to understand that we have a heat capacity. They usually say specific heat capacity on there. And sometimes instead of the letter C, you'll sometimes see them use the letter S. Don't be confused by that. But they're asking how much energy is needed to raise the temperature of 8.50 times 10 to the second gram block of aluminum from 22.8 to 94.6. So we are definitely dealing with a calorimetry problem. So let's write our equation out, which is Q is equal to MC change in T. And we're going to figure out the heat that is needed to raise this piece of aluminum from 22 to 94. So let's gather the information we have. And the first piece of information they give us is the specific heat. So I'm going to put it right underneath here. I'm going to go 0.900 joules per gram degree Celsius. Then they give us the mass, and that is 8.5 times 10 to the second grams. And then finally, they give us the change in temperature. Now, if you take a look at this, it really is 94.6 degrees Celsius, subtract 22.8 degrees Celsius. And again, let me remind you that this is always the final temperature minus the initial temperature. Now, if you get this all in here, then math happens and you end up with your Q being equal to 54927 kilojoules. Now, I'm sorry, not kilojoules, joules. And this is, of course, in a world where units or significant figures don't matter. But let me show you how we do some cancellation of units here. Do you see how here grams would cancel with grams, Celsius would cancel with Celsius, and the unit that's left is joules. But this is not typically how we leave answers. Whenever we're dealing with a Q problem, we typically will change that to kilojoules. So this would be 54. And since we only have two significant figures here, that 54 is actually going to become 5.5 times 10 to the third, because we're going to slide the decimal place. 1, 2, 3. Oh, I made a mistake there. 10 to the fourth, sorry, kilojoules. Now, if they then asked us to go one step farther and ask us to figure out the enthalpy, we'd have to convert, remember, the change in enthalpy is equal to kilojoules per mole. So we'd have to know how many moles of we had in this problem. And do you see how in the problem they give us the number of grams of aluminum? So if we knew the grams of aluminum, couldn't we convert to the moles of aluminum? Now, we're not going to do that because they didn't ask us for the enthalpy. They asked us for the energy. How much energy? And that is this formula right here. And that's where we can leave it like this. All right, in the next video, we're going to do slightly more complex problems like this. Hopefully this has been helpful. I'll see you in video number 5.